Okay, so today I am trying to add a little bit spice to our class lectures by taking them outdoors. So we talked about the Gauss Markov setup and mentioned that they have some advantage, at least in the case where we are working with y bar as the least square estimator. Now we shall see that if the assumptions are met, that is, those Gauss Markov assumptions are met, in that case, any least square estimator has certain good properties for any linear models. So let's quickly recall the Gauss Markov setup. So we had this thing y equal to x beta plus epsilon, that is any linear model, and I have reminded you about the sizes. So there are n rows and p columns. And the Gauss Markov assumption, the Gauss Markov setup has been written as y tilde 0 sigma square I, which is very much like the multivariate normal notation, where the mean is 0 and the covariance matrix is sigma square I, which captures two things in one notation. All the variances are the same, the diagonal entries are all sigma square, whereas all the off-diagonal entries, the covariances, are all 0. So all these things are uncorrelated. So assumption is only on the first two moments of epsilon. Now that's the Gauss Markov setup, but for the time being we shall make one further assumption, and that will be a simplifying assumption that we shall relax later, namely the X matrix, the design matrix, is such that X transpose X is an invertible matrix. In this case, least square estimator will be unique and is given by the simple expression beta hat equal to X transpose X inverse X transpose Y. We want to see various interesting properties or optimality properties of this particular estimator. Now observe that this is what is called a linear function of y. It is a matrix, a fixed known matrix, pre-multiplying the vector y. So our data were y, and we are pre-multiplying it by a known matrix. We want to find its expectation, we want to find its variance. For this, let's quickly recall how we compute expectation and variance. I mean, by variance, I mean the variance covariance matrix of a random vector. So suppose I am given some random vector, which I am denoting by this red vector, vertical little vector. It is pre-multiplied by a fixed matrix of appropriate order, which I am denoting by the cyan rectangle. So if I take expectation, then expectation just passes through this cyan rectangle and it will give you expectation of that matrix times that vector equal to that cyan matrix into the expectation of that particular vector. So the expectation will enter through, what should I say, that cyan matrix, so to speak. Okay, and if I am working with the variance, the situation is pretty similar, where the variance will enter through the cyan matrix. The result is you will take the variance term of this red vector, that will be a matrix. You will pre-multiply it by the cyan matrix, the constant matrix, and post-multiply it by its transpose. So remember, you are pre-multiplying it by the matrix as it is and post-multiplying it by the transpose. Now if you apply this result and the last one onto this beta hat formula, where this part is that fixed matrix and this y is that random vector, then it is pretty easy to check that expected value of beta hat will be just beta. So it is unbiased. Whatever be the value of beta, beta hat must be unbiased. So expected value of this should be beta hat. By mistake I have written just beta. In fact, not a mistake, the hat is there, which you can hardly see under the black line. And similarly, variance of beta hat, which is not very appetizing, it just happens to be sigma square times x prime x whole inverse. You just apply the formula blindly. in one line you will get these expressions. Now the first one is interesting because it says that beta hat is actually equal to the expected value of beta hat is equal to beta. Now when you do this, remember you are doing the simple thing. If you are taking expectation of y, what is that? Expectation of y means this being fixed, it will come out of the expectation plus expectation of y, which is 0. So expectation of y is simply x beta. Similarly, if you take covariance of y, what will that be? This is an added constant, plays no role. It is same as the covariance of epsilon, which is sigma square I. Using that, you will get variance of beta hat is this. Now, one interesting fact about this is we assume that x here is x prime x is non-singular. Now, if it so happens that it is very nearly singular, that its determinant is pretty close to 0, in that case, this thing is going to blow up because this has the determinant term in the denominator, and which is expected. So, if it is exactly singular, in that case, you are not going to get any unique beta hat. So, if it is nearly singular, you expect that it is sort of approaching towards non-existence, non-uniqueness, that is, it becomes highly variable. So, its variance goes up a lot. So, we saw that the least squares estimator, assuming that it exists uniquely, has some interesting properties under the Gauss-Markov setup, namely, number one, it is unbiased, and number two, it has the expression for variance. Now, we want to prove something along this line, that the least square estimator is the best estimator in some sense. Now, it is not true that it is the best estimator in general, but we want to give some restricted sense to this best. So, in particular, we shall work with only those estimators which are linear in the data, that is, some matrix times y. We already have seen that this beta hat does satisfy that property, and it's also unbiased. So, we want to work among all unbiased estimators that are linear unbiased estimators, and at the same time, since we want to talk about best, we want to say minimize the variance. Now, beta hat is a vector valued estimator, so its variance is actually a matrix. So, I cannot talk about one matrix being less or more than another matrix. So, instead, we shall work with linear combinations of beta. So, we will try to estimate not beta, but linear combinations of those beta i's. So, these things I will call C prime beta. Like if C is E1, that is the vector 1, 0, 0, 0, then C prime beta will be just beta 1. Similarly, if I take C equal to E2, then C prime beta will be beta 2. Now, if I work analogously with C prime beta hat, then quite obviously, following the same result, we can immediately see that whatever C I choose, expectation of C beta hat will be C prime beta, and variance will similarly be a quadratic form with this thing sandwiched between a C prime here and a C here. So at least this is a number. So it will be very nice if I can say that subject to certain conditions, this is the smallest possible variance that I can achieve. Remember, this is indeed just a number, so I can talk about larger or smaller. Now, there is an interesting theorem, a very important theorem of linear models to that tune, and that is called the Gauss-Markov theorem. The Gauss-Markov theorem, it says that start with the Gauss-Markov setup. Assume that your x prime x is non-singular. In fact, this condition may be dropped. So, ideally, I should call it Gauss-Markov theorem, simple version. If I drop this condition, that will be the general version. Then you take any C vector, then C prime beta hat, this linear combination of all the beta I hats, is the unique blue of the corresponding linear parametric function C prime beta. Now what is that blue? Blue means best linear unbiased estimator. That is, among all estimators that are linear in Y, that is a linear combination of the various observations Y, a matrix times Y, and that are unbiased. So among all the things that are linear and unbiased, this is the best, that is, it has the minimum possible variance. That is, the variance expression that we saw earlier is the minimum possible among all linear unbiased estimators. And not only that, this happens to be unique. That is, if you can give me any other linear unbiased estimator with variance equal to the variance of this least square estimator, then I can claim with probability 1 that your estimator equals this estimator. The proof of this fact is not very complicated, this theorem, but instead of presenting the proof directly, anyway the proof is given in so many books including our textbook, what we shall try to do is to provide the main geometric interpretation or the intuition behind the proof. The main argument of the proof happens to be very close to a well-known result, namely this result. Suppose I have a straight line like this, and I have a point outside the straight line, and I want to find out the least distance from the point to the straight line. And you know that the answer is, if you drop a perpendicular from the point onto the line, then that will give you the least possible distance. If you take any other line like this, any other arrow where the tip lies on the line and the tail lies at that point, the length must be greater than or equal to this. And not only that, this arrow, this minimum length arrow, also happens to be unique. Now how do you really prove this fact? The proof goes like this, that you just consider this as something like the defending champion, and you take any other line which you consider as the challenger. So you have the challenger and the defending champion. You want to show that the challenger, which also satisfies the condition that its tail is at the point and tip is on the line, must have length greater than or equal to the defending champion. And the way is to use Pythagoras theorem. You just consider this, which basically means you break up the challenger into two parts, the champion plus whatever you get when you subtract the champion from the challenger. So the challenger is champion plus this red vector. And then you notice that this is 90 degree. So if you just apply Pythagoras theorem, you see that squared length of this is squared length of that plus squared length of this. You really do not need to compute squared length of any of these things. You just observe that squared length must be greater than or equal to 0. So squared length of this fellow must be greater than or equal to squared length of this. And that immediately shows this must be having the least possible squared length. How do you show uniqueness? The same idea. Suppose there is some challenger which attains the same squared length as this champion. What does that mean? The same argument shows that this thing must have squared length 0. That is, this vector, this red vector, must shrink to a single point, which immediately says that this tip must match with that tip, so the challenger must be same as that existing champion. Precisely the same idea is applicable to the proof of the Gauss-Markov theorem. In this case, we consider as our champion the existing thing as C prime beta hat. So we are trying to show that this C prime beta hat happens to be the best possible linear unbiased estimator. That is, if you take any other linear unbiased estimator of the same quantity, C prime beta, in that case, you cannot have anything which has got smaller variance than C prime beta hat. Okay, so that is the existing champion, the defending champion. Now suppose you have got a challenger. The challenger must again be an unbiased linear estimator. Since it is linear, it must be a linear combination of the observations, namely the yi's. So it must be of the form L prime y. So that is the challenger. It also must be an unbiased estimator of C prime beta in order to qualify to be a challenger. So I assume that I have one such challenger. Now I will use precisely the same idea as I used for showing that the orthogonal distance is the minimum distance. What I will do is that I will split this challenger L prime y into two parts. The part which is our defending champion plus whatever is left out. So L prime y is C prime beta hat plus L prime y minus C prime beta hat, which is just trivial. C prime beta hat cancels off. Now my plan is to show that the variance of this, so I am using variance in place of squared length in the geometric example. So my aim is to show that the variance of this is same as variance of that plus variance of this, which means I am assuming that the covariance, I am claiming, not assuming, that the covariance of this and this must vanish. If I can have that, then immediately the result will follow. Simply because I know that variance must be non-negative. I really do not need to compute the variance of this quantity or the variance of this quantity or the variance of this quantity. I know since the variance of this is non-negative, variance of this quantity must be greater than or equal to variance of this quantity. The only thing that I need to show is that they are actually uncorrelated, that their covariances are 0. That's a very simple exercise. You just compute the covariance and you will see, boom, it becomes 0. Two-line argument. Now you might wonder, how is that possible? Because we had some C and some L. There must be something which relates that L with C. Otherwise, how can I expect that these two things will be 0? Well, there indeed is one such relationship, because remember, we have the fact that L prime y was a challenger, which means it is an unbiased estimator of C prime beta. So you just expand this expectation, equate that to C prime beta. You remember that this is true for all beta. That's why I have written this identity sign. So just equating this, you will get a simple expression relating the vector L with the vector C. Plug that in the covariance expression of these two. Just do it. In one line, you will see there's a massive amount of cancellation and you are left with nothing but 0. Try to do it yourselves. You can find it in our textbook, but it's fun if you try to do it yourself. Once you have that, you understand what we got. We have that this variance of this equals variance of this plus variance of this. That means variance of this must be greater than equal to variance of this, and that shows that this must be having the minimum possible variance. Now, how do I show uniqueness? Again, the same idea as our geometric example. If you find the variance of this is equal to variance of this, then that immediately implies the variance of this must be 0, because variance of this equals variance of this plus variance of this. These are all non-negative quantities, so this has to be a 0. And a variance being 0 means that the random variable must be a constant random variable. So this must be a constant random variable. To be entirely precise, I should say with probability 1. Okay, so with probability 1, this has to be constant. What is the constant? Very easy. I have already told you this is unbiased. We have checked that that is unbiased. So both of them have the same expectation. So expectation of this difference must be 0. So it's a constant quantity whose expectation happens to be 0. So the constant quantity must be equal to 0. So this quantity, the challenger minus champion thing, must be equal to 0. That is, challenger must be same as champion. And that shows the uniqueness part of the theorem.